Good morning, afternoon, evening, whatever applies to you, ladies and gentlemen. My name is Lawrence Henry Nieves. I'm an electrical engineering student at Florida International University, and today I will be discussing with you topics related to routers and routing protocols to provide a rather basic overview on how these devices function, how they apply to our modern networks, including the internet. So, without further ado, shall we delve into this very interesting topic? A router is a networking device utilized to facilitate the communication between two or more separate networks. Routers are deemed intelligent devices in that they are able to use information they acquire through various means, which will be discussed later in this presentation, to make decisions about which pathway is the most ideal to transmit information across. The information transmitted by routers are known as packets. The modern router may possess functionality of multiple networking devices, including that of a wireless access point or switch. But at its core, the most important function of the router is to connect multiple separate networks together. And without routers, there would be no internet as we know it. Let's take a very, very simple look at what the job of a router is. Now, let's say this right here is our router. Connected to one end of this router, we'll make it very simple. We have a single computer. And we'll say this computer right here belongs to what we'll call network number 1. Now, our computer on network number 1 wants to talk to another computer that belongs to an entirely separate network connected to an entirely separate router. And we'll call that network network 2. Right here. Now, our two routers in this diagram will take any messages from network 1 or network 2, depending on who's sending and who's receiving, and make sure it reaches the other network. So right here, we have, let's say our computer on network 1 wants to communicate with network 2. It'll send its packet along the line to the router. The router will take a look at the packet, read where its destination is, and make a decision and decide it has to be sent out the other end along this pathway between the two routers. Now the second router will receive the packet, will take a look at what its destination is, and will decide it has to be forwarded along outside to the other interface until finally our computer on network 2 receives the packet. Now, it's important to take into account here that there are actually 3 networks in this diagram. A connection between two routers is actually its own separate network. And we'll call this network 0. Right here. The process by which routers make their decisions is known as routing. In order to make these decisions, the router possesses a table filled with entries about other networks the router is aware of. Entries in this table can either be assigned statically or dynamically, which we will discuss next. Static entries in the routing table must be manually configured by whoever is administrating the router. These are given the highest priority by the router, but are extremely time-consuming to configure, and for most practical purposes have been shunned by dynamic routing. However, they still have their applications, including that of the default route, which is a route given to any packets that the router receives from networks it is not familiar with. Without a default route, the router will simply drop these packets and they will not be sent anywhere at all. Now you may be wondering, why would you even bother using a static route if you have to manually set up everything? It seems like a hassle, doesn't it? Well, there are two main reasons you would probably use a static route for. Number one would be security. Let's say we have, for example, a military network composed of multiple smaller networks. On one of these smaller networks, we have, let's say, a research and development server. On another network, you have a budget server. On the third network, subnetwork, you have a server where the military issues press releases. Now, you would never want any of your classified research and development information to go directly to the press, now would you? Now, with the static route, you could define it so that your traffic from your network that it contains a research and development server only goes to, say, subnetwork number 2, which is where your budget is, to see whether or not you can afford to continue with this research and development. For example, here's our example network. Here we have our research server, and we want to transmit traffic to the budget office, see whether or not we can afford to continue research. But our research needs to remain classified. So with a static route, we can tell this router right here to only transmit traffic from network 1 down to network 2 and make sure it never goes to network number 3. For the most part, a lot of secure government networks are made this way. It's very tedious to configure, but ensures your messages stay on the path that you want them to. The second reason, which was discussed in the slide briefly, was the default route. Now, without a default route, if you received a packet from an unknown network, the router would simply trash it. With the default route, you can tell the router, hey, I don't know where this packet is from, but maybe I want to send it down this way for whatever reason, security, etc. Ultimately, it's up to you to decide whether or not you want to accept unknown packets, though. Utilizing what's known as a routing protocol, or a method of sharing information between routers, routers can develop their own entries for their routing tables, and can change them as needed without any input whatsoever. As a whole, dynamic entries using routing protocols are easier to use, and for most purposes are more efficient, especially on larger networks. Routing protocols allow multiple routers to share information about their routing tables between one another to help determine what is the best possible path to utilize for transmitting packets. Routing protocols require a value known as a metric, which is used to help determine what this best path may be. Depending on what protocol you're using, the metrics can vary from anything from the speed of the pathway, how much bandwidth, to even the actual monetary cost of using that pathway. Routing protocols also require an update method, or a means by which information is shared between the routers, and this will also vary by protocol. Large organizations assigned an IP address by an internet service provider on the internet are also given what is known as an autonomous system number. An autonomous system may be made up of one large massive network or a bunch of smaller networks. Routing protocols used within an autonomous system are known as interior gateway protocols, or IGPs, and routing protocols used to connect autonomous systems to one another, such as over the internet, are known as exterior gateway protocols, or EGPs. Let's quickly run through a simple diagram to explain autonomous systems and compare interior gateway protocols with exterior gateway protocols. Here we have a diagram of two separate autonomous systems that are both connected to the internet. Autonomous system number 1 is made up of a bunch of smaller networks, and it utilizes an interior gateway protocol to set up routing entries amongst the different subnetworks. Once it connects to the internet, it has one router on the edge, which connects directly to the internet for it. And in order to communicate with Autonomous System 2 and any other autonomous systems across the network, or across the internet, it requires an exterior gateway protocol. In order for this router at the edge of Autonomous System number 1 to get information from the router at the edge of Autonomous System 2, you require an exterior gateway protocol. While both Autonomous System number 1 and 2 within themselves use interior gateway protocols. Interior gateway protocols can fall into one of two major categories depending upon what method they use to update their routing tables. First are distance vector protocols, which share the whole of their routing table's information with their neighbor routers. Second are link state protocols, which only share information about the networks they are directly connected to, and then share packets all across the network until a map of the entire network is created from these smaller packets. One of the first distance vector protocols to be utilized was the Routing Information Protocol, or RIP. RIP utilizes a hop count as its metric. A hop count can most easily be described as the number of routers a packet must pass between before it reaches its destination. As RIP only supports a maximum network size of 15 routers, it is most well suited for smaller networks. There are two versions of RIP, RIP version 1 and RIP version 2. RIP version 1 is classful, while RIP version 2 is classless, which we will describe what exactly that means in a few moments. Let's take a look at the functionality of RIP. Now, RIP uses a metric known as a hop count, which in the most basic terms is the number of routers a packet has to cross before it reaches its destination. So let's take a look at this diagram. Right here, we have a computer connected to a network on router number 1. It wants to reach the computer on router number 3. Now, as you can see, router 1 has two different paths it can take. One that takes it from router 2 and then to router 3, and one that takes it between routers 4 and 5 to router 3. Now, RIP will take a look at its entries in the routing tables and determine that the best path, based solely on hop count, is to path number 1, to jump between router 2 and router 3, because it has to cross less devices along that path. Now, since RIP is a distance vector protocol, router 1 also, when it's time to make any updates or changes to the network, sends the whole of its routing table, which will include information about routers 2, 3, 4, and 5, after it's received information from other routers, to its neighbors. The issue with the distance vector protocol is that because the router is sending its whole table, if you have too many routers connected to one network, that will take up a lot of your space because you're sending your whole routing table, which could, in RIP, could include entries of about 15 routers, not to mention all the paths in between them. If you combine that with the rest of your network traffic, you can actually potentially take up a lot of bandwidth, which is why distance vector protocols are best suited for small to medium-sized networks. The most widely adopted link state protocol is known as Open Shortest Path First, or OSPF. The metric utilized by OSPF is relative link cost, which can be configured to take into account bandwidth, speed, etc., depending on whatever the end user requires for their network. It is also a classless routing protocol. OSPF functions by separating the network into smaller sub-areas. Routers within a sub-area share information about their area, while routers at the edge of different areas will share information with one another about their respective areas. And Area 0 is also required to be defined to indicate the network backbone, or the portion of the network in which multiple subnetworks are connected to one another. Now, let's take a look at the link state protocol, OSPF. Now, OSPF divides a network into smaller sub-areas, and because it's a link state protocol, routers only share information about the routers they're directly connected to, as opposed to their entire network tables. Now, this means that the amount of information sent between routers and updates is much smaller than with the distance vector protocol. But it also means, eventually, every router will get a sort of logical map of what the network looks like, and thus can determine what paths to take based upon the established metrics. Now, OSPF requires an area 0 for the network backbone, or the section where all subnetworks are connected to one another. Here. Then each of the individual routers might have its own sub-area, areas 1, 2, 3, 4, 5, 6, so on and so forth. Now, when it comes time to update, router 1 will tell other routers, hey, I'm connected to router 2 and router 4, even though it might know, for example, router 2 is connected to router 3, but it doesn't need to remind router 2 it's connected to router 3, because router 2 already knows that. Rather, it can simply just tell router 2, hey, remember, I'm connected to you, and I'm also connected to router number 4 in case your link between the two of you goes down. I have another path. Or if this path becomes too congested, you can always send things over here. This helps the network set up a sort of map of everything without actually having to tell one another every exact little detail, because it'll all come together over time. The Enhanced Interior Gateway Protocol, or EIGRIP, is a proprietary hybrid protocol devised by Cisco Systems that's currently in the process of being made open source. It utilizes elements of both distance vector and link state protocols. At the establishment of a EIGRIP network, entire routing tables are shared, but whenever a change occurs after that, these changes are reflected using partial updates. The metric for EIGRIP utilizes multiple different sub-metrics, including bandwidth and delay, and then uses a mathematical formula to create a composite metric. It is a classless protocol as well. Cisco's EIGRIP is a rather interesting routing protocol in that it contains elements of both the distance vector protocol as well as a link state protocol. Until recently, this protocol could only be used on Cisco's proprietary hardware, their own routers. But in recent months, Cisco has been making efforts to make their EIGRIP protocol open source so that it can be used on any device. Now, at the beginning of the establishment of an EIGRIP network, routers, like a distance vector protocol, share their entire routing table. But afterwards, we'll only share any changes. So, for example, to start, we'll share our entire routing table, and let's say later on, a router discovers two of its entries are no longer viable. They'll simply just share an update saying, I'm no longer connected to these two entries. Now, the metric utilized by EIGRIP is a composite metric that uses Cisco's own mathematical formula to take multiple different metrics together and develop this metric that represents the best possible paths, or the cost of an individual path connected. Like so. The most widely adopted exterior gateway protocol is the Border Gateway Protocol. The Border Gateway Protocol is absolutely vital to the functionality of the Internet, as it is a protocol entrusted to link different autonomous systems across the Internet with one another. Without BGP, there is no Internet. This protocol does not utilize traditional metrics. Rather, path rules and other policies are specified by whoever is administrating the specific router to their needs. It is also a classless protocol. The Border Gateway Protocol is the most widely adopted exterior gateway protocol. All we really need to know about it is that a router is assigned an autonomous system number based upon what organization it belongs to. It connects to the Internet and is able to share information with other autonomous systems, which is essentially what the Internet is made up of. many autonomous systems, each of which could possess any number of subnetworks, like so. So, for example, we may have autonomous systems 1, 2, and 3 here, but they all connect to the internet, to a cloud of other autonomous systems that all have to share information with one another to facilitate the communication all around the internet. Without BGP, very simply put, the internet would not exist, at least as we know it. It would require some other method of routing its information. Routers are incredible devices that have helped to make modern telecommunications possible. Without routers, we'd have no means to connect separate digital networks. We'd have no means to help determine what is the best possible path for which to route any information across said network. Now, we've barely just scratched the surface of routers in this minor overview. There's so much more to routers to think about. Technical specifications, whether or not they're optimized for one service over another, whether they're integrated with other networking equipment, what sort of communication mediums they support, etc., etc. But I hope that this overview allows you to at least get a basic understanding and appreciation for these devices that do so much work for us and make the modern age that we live in possible. So, next time you're in your internet, just think about it. At its core, the internet is just thousands upon thousands of routers connected to one another, making sure your packets get to where you want them to, and make sure you get your reply. Thank you very much for your time. I hope you've appreciated this presentation, and I hope it inspires others to hopefully take a look and learn a little bit more about information technology, telecommunications, to see how it all really works, how our world is interconnected. Because each and every day, the world is getting smaller and smaller thanks to technology such as routers. Thank you very much. Have a pleasant day.